Today we are talking about the force of gravity. We're going to talk about what affects it, what makes it stronger or weaker, okay? Things like that, how it can act as a centripetal force, right? But biggest thing about gravity is that it causes an attractive force between two objects, two or more objects, in fact, okay? So at this point, I'm going to make you all feel incredibly awkward. Yes. You are going to turn to somebody nearby you, stare deeply into their eyes, and say, I am attracted to you. And now that you all feel incredibly awkward, you can stop. Unless, of course, that didn't make you feel terribly awkward, in which case, well, okay, good for you. But you are actually technically attracted to that person, not in the way that you probably thought when you said that, but okay, you are gravitationally attracted to that person, but not very much. Okay, and we're not saying that to insult anybody, but you just aren't big enough to generate very much gravity. Certainly not to overpower the large gravitational field that we constantly live in, the one generated by the Earth. Okay, so the big thing here, guys, is that there are effectively two things that affect how much gravitational attraction there is between two objects, right? The mass of those objects and how far apart they are. Okay. Both of them have a pretty big effect on that, but the distance between two objects has an inversely exponential relationship with gravitational attraction. So if I were to double the distance between two objects, I would feel 1/4 the attraction between them. Okay, it's inversely exponential, right? Okay, if I move 3 times as far apart, then I would feel 1/9 the gravitational attraction I felt previous. Right? Now, consider that. Are some of the things in our universe pretty far apart? Yes. Okay. I mean, give you some idea here. Like the moon and the Earth are, what is it? Well, no, yeah, far, but I'm drawing a blank on the number right now. No, we don't want to do that. Okay, the Earth and the Sun are 1.50 times 10 to the 11 meters apart. Okay, that's on your formula sheet, average Earth-Sun distance, 1.50 times 10 to the, I think it's 11, okay, meters. Is that a long way? No. It's pretty far, okay? I mean, if the sun were to, like, just suddenly go out, it would take over 8 minutes for us to know, okay? We're pretty far away. I mean, light travels the speed of light. I mean, that's pretty fast. So if it took 8 minutes for it to get here, the Earth and the Sun are pretty far apart. But is there still a lot of gravitational attraction between them? Yes. So while the relationship between force of gravity and how far apart the objects are is inversely exponential, we are talking about huge amounts of mass when we're talking about, objects, celestial objects, stars, planets, and things like that. Okay, we're talking about huge amounts of mass. If we're talking about, 2 people in the classroom, we're talking about negligible amounts of mass. Okay, if you were out in interstellar space, as far from any other large object as you could possibly be, you wouldn't be able to attract a piece of dust towards you by gravitation, even if it was right in front of your face. It wouldn't move towards you because there's just no gravitation. The force of gravity between the two of you would be so small that it just wouldn't cause anything to happen. Now, that dust might actually move towards you, but not because of gravity, but because of static electricity. Okay, at that distance, the force of like static electricity and things like that would actually be way stronger than the gravitational attraction would be, right? Because the differences in charges and stuff. All right, so we got to learn the relationship between gravitational attractive force, mass, and distance. Okay, that's kind of the key thing for today. And obviously gravity acts as a centripetal force because we see that things orbit other things in our universe. Okay, and so that's what we'll be looking at there. All right, so who came up with this whole idea of gravity? Newton, or at least he's the one given credit for it. Okay. People knew about gravity long before that, but he's the one who gave it a name. He's the one that kind of explained it to people. And how did he explain it? Yes, he told that fake story about hitting in the head with an apple. Okay. No, it was just something he used to explain that he got in the way of the gravitational attraction between the Earth and the apple. Okay. Now, notice how he states that. The gravitational attraction between the Earth and the apple. He didn't say the Earth pulled the apple. because it isn't that way. The force of gravity is a mutual attraction. Okay, the apple is attracted to the earth, and that's kind of the part that dominates our thinking because the earth is huge, the apple is small, okay, and we only see the apple moving, right? Well, we only see the apple moving because the apple is small, okay? The earth is really big, but the force of gravity between them is the same, okay? The earth is just as attracted to the apple as the apple is to the earth, but the earth is way bigger, way more massive, so the acceleration of the earth is negligible. Yeah, negligible. But the acceleration of the apple is 9.81 meters per second squared. Okay. In fact, all things trapped within the Earth's gravitational field accelerate at that rate. All right. Everybody with me on that? Okay. Okay. So a weird thing about gravity. I weigh different amounts depending on where I am. Okay. On Earth. Yeah. On Earth. I can go to different places and weigh different amounts. All right. And that's not because my mass has changed or that the mass of the Earth has changed, but because I'm a different distance from the center of the Earth, depending on where I am. That doesn't mean the Earth is flat, because that's crazy. Okay? That's just crazy. Anyone who thinks that is also crazy. Okay? The Earth is not flat. Okay? But the Earth is also not perfectly round. The Earth is kind of oblong, actually. Not a lot, but just a little bit. Enough that there's a noticeable difference between how much you weigh at the equator and how much you would weigh at the North Pole. Because when you're at the equator, you're further from the center of the Earth than you are at the North Pole. Yeah, it is. But here's the thing. The Earth is not a perfect circle. Okay, so the Earth is not a basketball. It's also not a football. It's somewhere in between. Okay, it is slightly bigger. Oh, that's terrible. Yeah, the Earth's not an egg, but okay. Well, it's, I should draw it in two halves, and that might work better. Okay, so we'll go like, that's a little bit better. It's a lemon. Not really, but okay, it's not, this is greatly exaggerated, but you get the idea. The Earth's not perfectly round, and the Earth's not perfectly round because of the way it formed. Okay, when it formed, it was a molten ball. Okay, and it was spinning really fast, and just like a top when it's spinning, or a merry-go-round when it's spinning, you get that centripetal acceleration going outwards. Okay, so it kind of flattens at the top and kind of gets bigger in the middle, and you see that actually with basically every planet in the solar system. Saturn shows it better than anything else. Saturn is like really like visibly flat, okay, much wider at the equator than it is at the poles. All right, so if I'm standing at sea level at the equator, I weigh 684.6 newtons, okay, if I'm 70 kilograms. At sea level at the North Pole, I weigh 688.3 newtons, because I'm closer to the center of the Earth when I'm standing at the North Pole than I am at the equator. Okay, if I'm in Chicago, okay, so about, well, a little more than halfway between the equator and the North Pole, okay, but also at kind of a low altitude because it's near the Great Lakes, okay, 686.2. So I'm closer to the center of the Earth in Chicago than I am if I'm standing with my feet in the ocean at the equator. Right? If I go to the top of Mount Everest, where I should theoretically be furthest from the center of the Earth from anywhere else on Earth, I still weigh more. I'm actually closer to the center of the Earth standing on the top of Mount Everest than I am if I'm standing with my feet in the ocean at the equator. Weird, okay? But the Earth's that oblong. Okay, it's that oblong. And even though we think about Mount Everest being this giant mountain, okay, if you were to look at Earth from a distance, it would look about as smooth as a billiard ball. Okay, Mount Everest is not a really big deal, okay, when we're talking about kind of differences between the center of the Earth and the highest point. Now, you look at a planet like Mars, and it's visibly different. Okay, Mars looks like it has a tumor. Okay, where the Olympus Mons and the Tharsis region, where all the volcanoes are on Mars, it's like visibly humped. Okay, in that area. So those are like huge. Okay, in terms of the difference. Okay, so here's the center of the Earth, right? Okay, so if I'm at the North Pole, I'm just going to draw a line so I can maintain its length here. Okay, so if I'm at the North Pole, that's how far I am from the center of the Earth. But if I go, oh shoot, that's going to make it longer. If I go to the equator, right, I'm further from the center of the Earth now. Okay, and so I'm lighter because I've increased essentially my distance from the center of the Earth's mass. Okay, I mean, obviously the Earth's mass is everywhere, but that's the center of it, and that's what we always use is center to center. No, that 9.81 value, it even says on your sheet, is average acceleration due to gravity. Okay, here it's about 9.83. Okay, you go to the North Pole, it's about 9.84, 9.85. Okay, sea level, it's like 9.78. Okay. Yes, and in fact, you will notice that if you look and watch carefully at the Olympics, anytime the Olympics are held nearer to the equator, more records in throws and jumps and runs are broken than if they are held at more northerly locations. Okay, like for example, there was a long jump record that stood from 1968 to 1996. Okay, the Olympic long jump record. And it was set in Mexico City, which is not only near the equator, but also at a high altitude. So he had everything going for him, came unglued on one jump, okay, and broke the record, and it stood forever and ever. Okay, and then it was broken in 96 just because, and it was actually broken, 96 was in Atlanta, right? I think so. But I mean, so, you know, it's not near the equator, but training had just gotten good enough. Everyone was getting close, okay, but it stood for a very long time because, you know, it was set in the perfect location. Okay, so is that kind of making sense there? Okay, we're seeing the effect now. If I go into low Earth orbit, so I'm on the International Space Station, okay, I still weigh 647 newtons. Okay, obviously lighter than if I'm standing on the surface of the Earth, but I still have weight. I'm still attracted to the Earth in low Earth orbit. That doesn't change. Okay, the Earth still exerts. There's still a gravitational attraction between me and the Earth. Okay, if I'm not moving fast enough to stay in orbit, I'll fall back into. Okay, that's what happens to satellites when they can't move fast enough. They fall back in and they burn up. Okay? Yes, they're always falling. Okay, when we talk about satellite motion, that'll make a little bit more sense. But to get something to orbit the Earth, essentially you have to make it go fast enough that the distance it falls is also the distance the Earth curves away, because the Earth is round, not flat. Okay, but yeah, that's how you make something orbit the Earth, is you make it so that it goes fast, about 8 kilometers per second near the Earth's surface. Okay, out in orbit, it's slower than that. It's about, I can't even remember what it is, but it's slower than that. The further away you go, the slower it is. Okay. If I'm in high Earth orbit or geosynchronous orbit, okay, so that's where we put all our GPS satellites and things like that, okay, and our communication satellites, we put them out in geosynchronous orbit so they stay over the same point on Earth, right, all the time. So what's their orbital period? 24 hours. And if you're going to stay over the same point on Earth, your orbital period has to be 24 hours, right? That way you orbit at the same rate the Earth spins. Okay? But to do that, you have to be way further out. But even in geosynchronous orbit, you still weigh 15.5 newtons. Right? But notice, we took a jump from here to here. Did we suddenly make the separation distance a lot bigger? Yes. And remember, that's an inversely exponential relationship. Okay? So we got a lot less gravitational attraction. Right? No. Well, in relation to the Earth, yes. Okay, if I get, like, here's the moon, right? So if I get to this point here where I'm close enough to the moon that I'm more attracted to the moon than the Earth, then from the Earth's point, from my perspective, my weight on Earth would be negative, because I wouldn't be heading towards the Earth, I'd be heading towards the moon, but we would never express it that way. Okay. So if you're like out in the Oort cloud, okay, if you're out in the Oort cloud, okay, your weight would be about 10 to the minus 8 newtons relative to the Earth. It would be something a little bigger than that relative to the sun, right? Otherwise, there wouldn't be debris still orbiting the sun out in the Oort cloud. Okay, so the big thing here, guys, is that in order for there to be weight, two objects have to be interacting. Okay, an object can't have weight until we refer to something else, because weight is the gravitational attraction between two objects. Okay, and they will exert a mutual attractive force. That's the key, mutual attractive force upon each other, okay, called gravitational attractive force, right? So yes, the moon orbits the Earth, but the Earth is just as attracted to the moon as the moon is to the Earth, okay? It's just that the moon is smaller, so we see its movement more. But actually, the Earth is also moving because of the moon. Okay? We simplify this relationship a lot and we say that the moon just orbits the Earth. But in actual fact, the moon and the Earth orbit a common gravitational center that is just below the surface of the Earth. Okay? So the Earth actually wobbles back and forth, trying to orbit that point. That's also the point the moon orbits. Okay? So the moon's orbit isn't a perfect circle. Okay? The moon's orbit is elliptical. Right? In fact, most orbits are at least somewhat elliptical. There's basically none that are a perfect circle. Okay? Everybody all right with that? Okay? So if you were to actually watch the Earth orbit the sun, okay, so here's the sun, okay, the Earth's orbit would not look like this. The Earth's orbit would look like this. Okay, and it would be ellipsoid, a little bit more ellipsoid than that. Right? So there are actually times in our orbit where we are further from the sun than others. Okay? And for us, that's actually the summer. Okay? We're actually further from the sun in the summertime because for us, the seasons are not caused by how far away from the sun we are because it's actually not that big a change. It's the tilt of the Earth. Okay? We're actually closer to the sun during our winter. Okay. But yeah, the Earth's orbit is not a perfect circle, which we'll talk about tomorrow. Okay, and it wobbles back and forth due to the gravitational pull of the moon. The gravitational pull of other planets in the solar system can affect it as well. Okay, so there are points where we're closer to the sun than others, and where we're moving faster. Okay, there's some points in the Earth's orbit where it moves considerably faster than other times. Okay, because it's closer to the sun. All right, so is that making sense? Yeah. Okay. So this is Newton's universal law of gravitation. Why Newton is given credit for that, I still don't quite understand. He came up with the idea, but he never made it work mathematically. Okay? Cavendish, a guy named Cavendish made this work mathematically. I'll show you how he did it. Okay? Newton understood that there was a gravitational attractive force between any two masses, and that's how he explained the apple falling to the ground. But he couldn't make the numbers work with the idea that he had because he knew that the relationship had to be based on the mass of the objects, which is why we multiply the two masses together on the top of this formula, and the square of their separation. Okay, we call it r because it's usually a circle. It's usually one orbiting the other, but it's actually separation distance from center to center. Okay? He couldn't make this work because he didn't have this number, big G. Big G is the universal gravitational constant. Okay? It's the number that effectively makes our kind of basic celestial mechanics work. All right? The reason Newton couldn't calculate this number is because the Earth's gravity always got in his way. He could never remove the Earth's gravity from any experiment where he was trying to find the force of gravity between two objects. The Earth's gravity was always overpowering, and he was never able to measure it. Okay? What he didn't figure out was something that Cavendish figured out. If he could make his experiment happen perpendicular to the Earth's gravity wouldn't be a factor anymore. Okay? But it took quite a bit of thinking to figure out how to do this. All right? So basically what we're saying with this formula is this. Okay, we multiply the whole thing by the universal gravitational constant, which is on your formula sheet. It's 6.67 times 10 to the minus 11 Newton kilogram squared. No, Newton meters squared per kilogram squared, I think are the units, right?
Newton meters squared per kilogram.
Per kilogram squared. You won't have to remember those. We never use those units for anything, okay? This is just the number you're going to have to plug into this formula when we use this formula, okay? 6.67 times 10 to the minus 11. Without this number, all of Newton's calculations were saying that everything should be crushed, okay? Because this is a very small number, and he's multiplying numbers here and then dividing by this separation distance and getting, that a person like myself should weigh thousands of newtons. Okay, like a crushing thousands of newtons, and that's not right. So he could never make it work mathematically. He knew he was missing something. Okay, so what this formula says is that there's a linear relationship, okay, or that the mass of the object is directly proportional to the force of gravity. If I have twice as much mass, I will have twice as much gravitational attractive force. Okay, but it also says that there's an inversely exponential relationship between separation distance and the force of gravity. If I double the distance between the two objects that I have, I will have 1/4 the attractive force between them. Right. Yeah, if you got close to a black hole. Yeah. I'm going to show you his experiment here right away. Yeah. Okay, so is everyone clear on the relationships there? Okay, the more mass you will have proportionately more gravity. Okay, the distance, you'll have exponentially less. Okay, so G is a number that we call the gravitational constant or universal gravitational constant. Here's the value, okay, 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. It's extremely small, so the gravitational force between two objects like your body and a baseball is so small that you don't notice it, okay? The ball doesn't fly towards you, okay? I think somebody once asked me though, so Mr. Coderre, if I kept eating, and got really, really fat, would food come to me of its own accord? And I'm like, theoretically, yes. Practically, no. Because in order for food to be attracted to you versus the Earth, you would have to have a mass somewhere on the order of the Earth's mass, which means you ate much of the Earth. So, challenge accepted, I don't know, but okay, yeah. Theoretically, yes, if you got big enough, you wouldn't have to get up to get your food anymore, but you might not be able to select what you eat because everything would be attracted to you, not all of it food, okay? Like rocks and recliners and, things that you probably don't want to eat, but you would have to eat if you were going to get big enough for things to be attracted to you by gravity, okay? So I don't know, I'm trying to envision how you eat a recliner, and then I'm actually thinking, how do you get that out? Oh, okay. Well, here's a real hole in that, because anything that comes out of you is still going to be attracted to you. Don't do that. I hadn't thought of that. That's a major problem, flaw in the logic there. Okay? Yeah, everything is attracted to you, including all of your waste. What's that? Yes. Yes, but everything would be attracted to you, so you'd be stuck with it all. Yeah. Okay. All right, we'll get off of that idea. Okay, here's Cavendish's experiment. Okay, and Cavendish's experiment looks pretty simple, but it was ingenious. Okay, what he did is he set up what's called a torsion balance. Okay, so he had this rod that was kind of on a pivot. Okay, and he had these big lead spheres, big heavy balls of lead. Okay, that were on here. And then from the ceiling, he had a torsion fiber, which is like a thin wire. And because he knew what it was made out of, he knew its tensile strength, okay? Which meant if it twisted, he would be able to measure the degree to which it twisted and then calculate the amount of force that was needed to do that because he knew how strong this stuff was. Everyone kind of follow there? Okay, because he could take this thing and just with his hands turn it a certain angle and then from that angle calculate how much force he had applied to the torsion fiber. Well, he said, if I can do that with my hand, I can let it go and let gravity pull it. The gravity between the lead sphere and this little tiny, they're made of pith. They'd have been like a styrofoam, kind of like that, okay, really light. If they're gravitationally attracted to each other, the torsion fiber will twist. I'll be able to measure the angle it twists, and then I'll be able to calculate how much force there was between these two objects. Okay? By doing it this way, he eliminated Earth's gravity as a force. The objects aren't moving vertically. So the only force acting on them was, or that was causing the acceleration, was the force between them. Okay, so he found a way to run this perpendicular to Earth's gravity and thus remove Earth's gravity from the equation. Okay. Now, he obviously didn't have a laser, okay, because Cavendish lived hundreds of years ago, okay, but he basically had a light source, and it reflected off this mirror. And before everything got started, they were right on each other, okay, and then as the experiment went on, the force caused the torsion fiber to twist and the reflection to go off this way. So he was able to measure this angle here, and from that, calculate how much force there was between these masses. Right? Since then, he was able to, he had this part of the equation now, okay? He had that force of gravity that Newton could never measure because Earth's gravity always got in the way. He was actually now able to calculate that thing that Newton didn't have because he knew what the masses were. He knew how far apart they were. Okay? So now he was actually able to calculate the universal gravitational constant that Newton never could. Okay? So it was an important experiment because now this formula governs all things celestial that we know of. Okay, if we're trying to calculate, the period of an asteroid or the path of an asteroid as it orbits the sun to see whether it would ever hit the Earth, this formula is part of that. Okay, if we want to send a satellite into orbit, this formula is part of that. Okay, if we want to land a spacecraft on another planet, that formula is part of it. Okay, it's crucial to all things related to gravitational attraction between objects. Okay, so this force of gravity is theoretically my weight. Agreed? If I'm talking about me, this would be my weight. So theoretically then, this should be true. Agreed? Right? As long as I'm where? On Earth. Okay? That's why we need this formula. This formula works fine provided I know what G is. But G changes. The further away from the Earth I get, the smaller little g becomes. So it's always changing. It's not a number I can rely on. This I can always rely on. I can always know how far r is. I can always know the mass of the two objects, and this number is a constant. Okay? So I can always use this formula to calculate the force of gravity between two objects. Right? So what we want to do here is just confirm. Now, are we going to get exactly the same number using both formulas? Probably not, but it's going to be really, really close. Okay, really, really close. Because remember, 9.81 is an average, right? It's an average of everywhere on Earth. But r is also not a constant number on Earth. Okay, the r that you have on your formula sheet is also the average Earth radius. Okay, so it's also an average. Okay, so if I'm 70 kilograms, okay, and I multiply that by 9.81, okay, so right, I get 686.7 newtons. All right, now I'm going to calculate my weight using Newton's universal law of gravitation. All right, so I'm going to plug those numbers in. So that's going to be 6.67 times 10 to the minus 11 times, what are the masses? Me and the Earth. Okay, so mass of the Earth, 5.98 times 10 to the 24 kilograms. Big, okay? Times 70, my puny little mass, okay? Divided by the average radius of the Earth, 6.37 times 10 to the 6 squared. Okay, because in that formula, r is squared. Everybody with me? Okay. This is where it gets hairy. You got lots of exponents. You're going to need brackets. You got to enter things carefully. Okay, really, really carefully. All right, so we've got in brackets here 6.67 e negative 11, 5.98 e 24 times 70 divided by 6.37 e6 squared. All right, so I had to enclose the whole top part in a set of brackets as well. Okay. Pretty close? Yeah, considering we use two numbers that are heavily rounded and average, okay? Like this 9.81 meters per second squared here that we use, like we say, is an average, but it's rounded off, okay? This number is really rounded off. Okay? And we're talking about the radius of the Earth. How many decimal places did I not even show here? Right, a lot. They would have made a pretty big difference, especially with that number squared. Okay, so this is going to give you essentially the same answer. Okay, all right. Somebody had a question back there. No. Okay. All right. So everyone kind of follow me on how that works. Okay. Now, gravity, we also know, can be a centripetal force. Okay, and we've seen that happen. We've seen this situation a whole bunch of times. Right. That's when we always get the square root of GR as our end formula. If this is true, can this also be true? Yes, and that's what we're going to use anytime we're dealing with a celestial object, okay? Or objects where we don't know what little g is, or any situation where we're not sure about little g. No, because theoretically, if I use the actual value for this, remember, this is an average, and 9.81 was an average, okay? If I use the actual values for that point, I would get exactly the same number, right? Because it wouldn't be 9.81, it'd be 9.75 or 9.79 or whatever, and then this number would be slightly different as well. Okay. All right, so we can set that up. This is going to be the basis for all satellite motion. And we talk about satellite motion tomorrow. That is the basis of all satellite motion, that the force of gravity is causing a centripetal force that causes an orbit to happen. Okay. All right, so let's say that astronauts took like a cantaloupe, okay, a melon, to the moon. And because they wouldn't do that, obviously, but let's say they did, okay, because they would take a dehydrated melon, because it's lighter. Let's say that its mass is 0.65 kilograms. The mass of the moon is 7.36 times 10 to the 22 kilograms, and the radius of the moon is 1.74 times 10 to the 6 meters. So considerably smaller, both mass and diameter, or radius-wise, okay, compared to the Earth. What is the weight of the melon on the moon? Okay, so can I use m times g? No, I don't know what little g is on the moon. I have no idea. Actually, I do, but I can't use it because I don't know exactly what it is. It's around 1.6, okay? But I don't know for sure. So I'm going to calculate the weight of the melon using this formula, because I do have these things. This will be the mass of the moon, okay? This will be the mass of the melon, okay? And then we'll have radius. Now the radius will actually be the moon's radius. I'm standing on its surface, so I can use the moon's radius as the separation distance between me and the center of the moon. Everyone okay with that? Okay. So that r is always the distance from center to center. Now, if you look on your formula sheet on the second side where it says other useful constants, okay, it'll say things like average Earth-Moon distance, average Earth-Sun distance. Those are center to center. Okay, so that, like that 1.5 times 10 to the 11 is from the center of the Earth to the center of the sun. Okay, the average Earth-Moon distance, center of the Earth to the center of the moon. These types of calculations are always done with the center separation distance. Okay. All right, so I'm going to plug in these numbers and calculate the weight of this melon on the moon. So I'm going to have 6.67 times 10 to the minus 11, big G, times the mass of the moon. All right, so 7.36 times 10 to the 22 kilograms times the mass of the melon, 0.65 kilograms, divided by the radius of the moon, 1.74 times 10 to the 6 squared. Okay. So when you're typing this in, after you punch in each number, double check, okay, that you typed it in right. Otherwise, you're going to be going back and changing stuff after the fact. All right, so on the moon, that melon will weigh 1.05 newtons. Because otherwise, if you don't, it makes the next number you put in part of the exponent of the previous one. Right, so I'm just enclosing them because I've gone like 10 to the power of this. If I don't end that with a bracket, it assumes every number after that is part of the exponent. Right, and does order of operations. It's a mess. So you have to enclose everything, just like you did with Avogadro's number in chemistry. Right? Yep. Okay, so you can see I started with a bracket with two sets of brackets and then enclosed the universal gravitational constant, then multiplied by the mass of the moon enclosed. Okay, the mass of the melon I didn't have to enclose, but I was just doing it out of habit. Okay, then I enclosed the entire top operation and then divided by enclosed the mass or the radius of the moon squared. Okay. So yeah, there's a lot of brackets. You really have to keep track of your brackets. Okay, but on the same token, once you get good at this, if you forget a bracket, you'll know because your answer will make no sense. Okay, it'll either be ridiculously big or ridiculously small. Okay, like if you were calculating, let's say, the weight of a person on Earth, okay, and you would get like something times 10 to the minus 12. Okay, like you obviously did something wrong. Okay. All right, so that's the weight of the melon on the moon. Oh, they just gave it to me. Yeah, it's right here. Yeah. Okay. Any other questions on how that one worked? Okay, very straightforward. All right, so this is just it typed out neater than my chicken scratch. Okay, so here's what Newton's first law says about an object. It says that an object will continue to move in a straight line at a constant velocity unless acted upon by an external unbalanced force. Okay, so for gravity to act as a centripetal force, there has to be a balance point between inertia and gravity. And that balance point is an orbit. Okay, because if there was no gravity, the object would just do this. It would whiz right past this object here because they wouldn't be attracted. There'd be no force between them. Okay, but there is a force between them. So the object has its velocity, but it's attracted to the other object. But it's got this velocity, but it's attracted to the object. Okay, so it's always moving and always falling, always moving, always falling, always moving, always falling. If you connect all these, what you get is an orbit. Okay, so an orbit is the interaction between the speed or the inertia of an object and how much it's attracted to the other object. Okay, so to get something into a stable orbit is actually fairly tricky. Okay, even the moon's orbit isn't stable. Okay, the moon is constantly moving further away from the Earth. All right, and every year it gets about 2 or 3 centimeters further away. Okay? I know that doesn't seem like very much, but the moon used to be a lot closer. Okay? Like way closer to the Earth than it is now. Right? And very slowly over time, it's going to move away and away and away. And that actually will affect the length of an Earth day because the moon actually has a gravitational interaction with the Earth that actually affects the spin of the Earth as well. Okay, a day on Earth, if you went back, 2.5 billion years or so, was actually much shorter. Okay, and that's because the moon was also a lot closer. So imagine we only see the moon go around the Earth once every 28 days or so. Okay, that's about how long it takes for it. So that's from new moon to new moon, right? Well, imagine that you saw that happen a couple of times a day. Okay, you go back a few billion years and that would have been the case. Yep. What would have been the effect on the tides then? Yeah, like basically the moon would have pulled the whole ocean way over there, and then as the Earth spun underneath it and the moon moved, like the whole ocean, you would have actually seen it look like if you had a container full of water and you were doing this to it and moving it around in a circle. That's what the ocean would have been doing. Okay, like it was just the moon would have been that close and pulling that hard. Okay, tides would have been much bigger and much more frequent. Okay, billions of years ago because of that. Okay, so what we were just talking about here, this is just the explanation for what we just talked about here, how this leads to the development of an orbit. Okay, right, so we can say that Fg equals Fc. Right, so what we're going to do is we're going to calculate the speed of the moon in its orbit around the Earth. Okay, we're going to see if we can figure out how fast the moon is moving as it orbits the Earth. And we're going to use this setup to do it. Okay. All right, so here are our givens for this calculation. Okay, mass of the Earth, 5.98 times 10 to the 24 kilograms. Mass of the moon, 7.36 times 10 to the 22 kilograms. Okay, average Earth-Moon distance, 3.85 times 10 to the 8, right? Mind like a steel trap. It's just always closed. Okay, and obviously big G. All right, so the moon orbits the Earth, which means there's a centripetal force. That centripetal force is gravity, right? But obviously not m times g, because I have no idea what little g is out where the moon is. Okay, it's obviously not 9.81 out there. Okay, question? Oh, sorry, I knew we were headed towards calculating velocity and I had that stuck in my head. Yeah. All right, so I've got mv squared over r, okay, my formula for centripetal force, is equal to big G times the mass of the moon times the mass of the Earth over r squared. Okay, I've got r's on both sides. Are they the same r? Yes. Okay, I mean, it's centripetal force, it's the radius between the Earth and the moon. Well, so is the separation distance in FG. It's distance between the Earth and the moon. So yes, it's the same r. I've got three masses though. Is there one that appears on both sides? Which one? The moon, right? The mass of the moon is on both sides, okay? The reason this mass is the mass of the moon is because the moon's the one moving in the circle. And whenever we're using centripetal force, the mass that's moving in the circle is always m. Okay, so we're simplifying a little bit to say Earth is stationary. It's not really, but we're going to say it is. Okay, and that the moon is the one doing all the moving. Okay, all right. So now I want to solve for v. I'm trying to find out how fast the moon is moving in its orbit. So what do I have to do with this r? Okay, so if I multiply that r over here, it will cancel, and the square will go away because those are the same r. I'm going to divide both sides by the mass of the moon. What will happen to the mass of the moon? Yeah, that's weird. It's almost like it doesn't matter. And it doesn't. Okay? At whatever distance the moon is, okay, or 3.85 times 10 to the 8, it doesn't matter what mass is out there, it has to move at a certain speed. Okay? It could be a garbage truck, it could be a basketball, it could be the moon. They would all have to move at the same speed because out there, they would all fall at the same rate. Remember, all things, regardless of their mass, fall at the same rate, close to the Earth's surface or far away. Okay? And that's what determines how fast you need to move. The further away you go, the slower you can move. Okay? The closer you are, the faster you have to move. So the International Space Station has to move really, really fast. Okay? It goes around the Earth once every 90 minutes. Our geosynchronous satellites have an orbital period of 24 hours. Okay? So the further away you go, the slower you can go and still maintain orbit because you're not being pulled in as hard. Okay? All right, so now we've got that. We've got the r's have canceled, okay, and we're left with just v, but we need to take the square root. So what we are left with is this. The speed is the square root of g times the mass of the Earth over r. Okay, that's what's left after we've moved everything. Okay, so we'll plug in our numbers here. Okay, v will equal the square root of 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24 mass of the Earth divided by 3.85 times 10 to the 8 meters, the distance from the center of the Earth to the center of the moon. Okay, again, here's where it gets hairy. Okay, punching in all these numbers and maintaining brackets and such. Need 3 brackets. Sorry, I had to think about it. Need 3 brackets. Oh, awesome. Didn't get an error. Oh, but I also didn't get the right error. No, I did square it. Oh, I wasn't supposed to. That's why. Okay. Yeah, because I'm an idiot. All right. Delete that one. And still got the same answer. What did I do wrong here? Or removed. Oh, I need to take that bracket out. Delete. And then put it there. That's better. Okay, see how much the brackets can screw things up? Yeah, you might be better off to do it a little bit at a time and then square root everything at the end. See what happens when you try and show off? Bad stuff. Okay, so here's the speed of the moon as it orbits the Earth. About 1 kilometer per second. Okay, so at that distance from the Earth, okay, and it's a long way from the Earth, the moon has to move, or any object actually at that point, would have to move at 1,017 meters per second in order to stay in orbit. Right? So obviously, where the International Space Station is, we move a lot faster. Okay? This is why things have to be put outside the Earth's atmosphere if they were going to orbit the Earth. Right. Yeah. Okay. You can't go that fast within the Earth's atmosphere. You would vaporize, which is why things that like meteors and stuff burn up when they come back in, or unfortunately sometimes spacecraft, okay, satellites and things like that, they burn up because they're going so fast that when they hit the Earth's atmosphere, there's so much friction that they just burn up. Okay. Everyone follow me on that? That's why we don't have satellites orbiting the Earth at ground level. It would also be dangerous because they'd hit stuff, but okay. All right. Does everyone follow what we did there? Okay, now once in a while you might also get like a situation where you have to put period into that, where we have to do the substitution stuff, but we'll talk about that a different day. Okay. All right, so gravity is kind of a big deal when we're trying to get spacecraft to other places. Okay, if we want to send something to the outer solar system, which we've done a number of times and we actually do fairly reliably, we can't do that with just the launch vehicle. Okay? It takes a tremendous amount of fuel just to get something out of Earth's gravity well. Okay, how many people have heard that term before, gravity well? Okay, so gravity well just basically means the area around the Earth where Earth's gravity is significant. Okay? It's a fairly large area. So we have to get something moving pretty fast for it to escape the Earth, right? What we call escape velocity. So we use the bulk of our fuel in the launch vehicle. Once it's out there, it's not moving all that fast. We need to make things move faster, otherwise they'll take decades, and still even do, okay, to reach outer places in the solar system. So what we do instead is we use gravity, and we send them towards other planets, and we let those planets accelerate them, right? It's called a gravity slingshot. Okay, if you've watched The Martian, you know that they did this. Okay, they used the Earth as a gravity slingshot and fired themselves back out to Mars in less time than it would have taken them otherwise. Okay, so essentially what's done is you approach another body and you come in kind of at a certain angle and then you go off at a different angle. Right now, if you're thinking law of conservation of energy here, don't, because it doesn't apply in the same way as it does on a roller coaster. Okay, I'm coming in, getting accelerated, and then going off at a different angle, so it doesn't apply in the same way. Okay, everyone kind of with me there? Right. So we can use other planets to get these gravity accelerations or gravity assists. Okay, and most often we use Jupiter for that. Okay, if we're heading something out into the outer solar system, okay, then we'll send it to Jupiter first, because Jupiter is big. Okay, and it does a great job of speeding up our spacecraft when we send them towards it. Now, from a law of conservation of energy standpoint, if it accelerates the spacecraft, What does it do to Jupiter? Yeah, slows it down a little bit. Okay, so every time we send something around Jupiter for a gravity assist, we make Jupiter go a little slower. Much slower? No, Jupiter's huge. It doesn't care. It doesn't mind giving up a little velocity for our little puny spacecraft to get from place to place. Okay, but it does slow down just a little bit every time we do that. All right, so what you see here in this diagram is all the space missions sent from Earth to other places in the solar system. Okay, and they're color coded. Okay, so there are, what does it say? The green ones, I can't even read it on there because it's so blown up, but I have it back here. Okay, so the green ones, the yellow ones are NASA. Okay, the red ones are the USSR/Russia. So we're going to group them together. Okay, and then we've got the kind of bluish one is the European Space Agency, and then purple ones are Japan, green are China, blue are India. Okay, and then the deep space missions, the ones that you see going past the outer planets there. Okay, the green one is Pioneer, the blue are Voyager, the light blue is Galileo, Cassini-Huygens is the kind of brownish one, and the really light blue one is New Horizons. Okay, that's the one that went out to Pluto. Okay, and actually on New Year's Day passed another Kuiper Belt object called Ultima Thule. Okay, and took more pictures of it. So they all originate obviously from Earth. Okay, the most visited body in our solar system is the moon. Okay, we've sent tons and tons of missions to the moon. Now, what you see here is, yeah, we've got this color coding, but we've got some light lines and some dark ones. The dark ones are failures. Okay, so there's that color coding, but darker is failed. So the moon, we didn't do too bad. The first few, obviously, in the early goings, we didn't do so well. Okay, lots of failed missions to the moon. Okay, not unmanned, obviously, but failed. Okay, and then we had, a lot of successes there for a while, and most recently, a lot more successes. Getting to the moon, while difficult, is not nearly as dangerous as it used to be. Okay, we've sent quite a few to Venus. Okay, and you can see that again in the early going missions to Venus didn't go very well. Most of them were sent by the USSR, okay, by the Soviet Union back then. So the problem with Venus wasn't so much getting there as surviving once you got there. Okay, Venus is much closer to the sun, so the level of solar radiation would fry the electronics of the spacecraft quite often. And the Soviets were trying to land on Venus. Okay, now to give you some idea, Venus's atmosphere is 100 times thicker than Earth's. Okay, in the same way that Mars is 100 times thinner, okay, Venus is 100 times thicker. Right, so trying to get something through that atmosphere without it burning up is a problem. Getting something through that atmosphere without it being crushed like a pop can is another. Okay, that was the bigger problem. We could build a heat shield that could survive the heat, but we couldn't build something strong enough, at least at first, to survive the atmospheric pressure. The pressure from the atmosphere on the surface of Venus is stronger than the water pressure at the deepest point in the ocean on Earth. Okay, so like our strongest submarine would be crushed well above the surface of Venus. There's so much atmospheric pressure. Okay, so the first few of the Venera probes that they were called from the Soviet Union, they would descend through the atmosphere, sending back all this wonderful data, and then they would just stop because they would just get crushed. Okay, so the Soviets kind of eventually figured out how to fix that. I'm sure a few Soviet scientists ended up in salt mine in Siberia, okay, for failure, but they eventually got to the point where they did successfully land the probe on the surface. Now, it's not going to survive very long. It's hotter than the inside of your oven on the self-cleaning cycle, okay, on the surface of Venus. Okay, so these things are not going to survive very long, but they're going to survive long enough to do a couple of things. Take a picture and take a quick touch soil sample. Okay, that was all. They had a robotic arm that was just going to fly down like this and touch the surface and take some magnetic readings, figure out how much like the iron and silica content, whatever, of the rock. Okay, so first lander, it's got the camera right above the robotic arm. Now, there has to be a cap on the camera to protect it during descent and all that kind of stuff. So probe lands, lens cap pops off, they take the picture, and then the robotic arm flops down to sample the only thing brought to Venus from Earth. The lens cap. Design flaw? Maybe. So the next time they offset them by a couple of degrees so that the robotic arm. So the first mission that landed there was a total waste other than getting a picture of the surface of Venus. It only sampled the only thing brought there from somewhere else. Okay? Because they're like, what this? What this? This not. This is a refined metal. How are they refined metals? Oh, it's a lens cap, you idiots. Yeah. Okay. So yeah, that didn't work out so well. But they did eventually get several things to land successfully, and more recently we've had orbiting probes that have been mapping infrared stuff through the atmosphere and the surface and stuff like that. They just offset them by a couple of degrees. It was a round probe, so the camera would have been slightly offset from the arm, so that when the lens cap went off, it didn't hit the same place, right? But it had a wide field of view. Okay, missions to Mars. Okay, we're still having trouble with that. Okay, landing on Mars is tricky, really, really tricky. Okay, it has basically Mars has a jinx. Okay, only about half of the missions sent there to land are actually successful in doing so. And the issue there is that there's so little atmosphere, right? So we have to get things to slow down really quickly, and then there's all kinds of different landing mechanisms that we've tried. Some of them work, some of them don't. Some of them work sometimes, some of them work all the time, or more often. Okay, but we're getting better and better at it, but it's still a bit tricky because we've had even recently some that didn't work. Okay, most recently we had the InSight probe, okay, that landed there, and it's the one that's got a seismometer, so it's measuring Mars quakes and the internal temperature of Mars to see if it's still tectonically active, okay, things like that. So it most recently landed, but now what we're using for basically every probe is the Sky Crane lander. That's what they call it. So it's a ring of rocket engines. So the initial descent vehicle has two sets of parachutes. Okay, there's the high atmosphere parachute. Okay, that'll slow it down to like Mach 3. Okay, so it's a supersonic parachute. And then lower down the atmosphere, a second parachute is deployed to start the kind of more classic falling with a parachute on kind of falling. And then they have the rocket engines, which are the final descent stage. So the rocket engines are entirely controlled by computer. They cannot be fired remotely from Earth. Why? Exactly. Okay. In the best situation, it takes almost 35 minutes for a round trip there and back signal from Mars to Earth. Okay, so you can't land something remotely when it takes 35 minutes for the message to get there. Okay, you just can't do it. So it all has to rely on the computer making the right decisions. So the computer has essentially a more complex version of how your phone decides which way you're holding it. Okay, a gyro inside that tells it information about how it's oriented, and then it fires the engines to keep it level. And then it slowly descends down, and then it's actually lowered from that ring of engines. That ring of engines just hovers and lowers the vehicle down on a cable. And then just before it reaches the ground, they cut the cable. There's a small explosive on the cable that breaks the cable, and then the rocket engine just goes flying off. Okay, because what do you not want the rocket engine to do? You don't want it to land on the lander. Okay, so that's the best way to do it is when it's still about 10 feet above ground, they just sever the cable. Spacecraft falls the last 10 feet on Mars, not as bad as falling 10 feet on Earth. Okay, it's 1/3. It's like falling 3 feet. Okay, so it falls down there, and then the rocket engine just kind of flies off and crashes somewhere else. Okay, we don't worry about it; just goes and crashes. Obviously, the difficulty there is everything is done by the computer, and computers don't always make the right decisions, or something happens to the computer during the rough, descent, shaking, and all that kind of stuff. That's usually what goes wrong. Okay, what we did before the Sky Crane was the airbag landing system. Yeah, just balloons. Yeah. Okay. So the whole lander would be encased in these airbags. Okay. So it'd be descending by parachute, and then poof, all these airbags would inflate, and then the parachute would come off, and the thing would just bounce along the surface on these giant airbags, and then kind of roll to a stop. And then the computer inside would say, okay, so we're upside down, so we want to deflate this balloon, this balloon, this balloon, this balloon until it rolled back over the right way. Okay. It actually worked pretty reliably. Spirit and Opportunity both landed with the airbags. Curiosity was the first one to use the Sky Crane, and we've done the Sky Crane on everything since because it seems to be more reliable. The airbags, the problem is that there's a maximum size. You can only land something so big with airbags because otherwise it tends to break them. So the Sky Crane can land big landers, and that's what we've been landing more recently. Curiosity is the size of a golf cart, right? Whereas Spirit and Opportunity were much smaller. No, the Spirit and Opportunity both functioned for a very long time. They had a like 90 days is what they were guaranteed for, and one of them operated for 5, the other for 10 years. Yeah. So now NASA's like, okay, that 90-day warranty thing, that's crap. Okay, you can guarantee this thing for a little longer than that. Okay. The big thing for them was they didn't know how long it would take for the solar panels to be obscured, and that is ended up what killed them both was that the solar panels just got too covered, and then the heater that kept the battery alive would die, and then the battery would die, and they wouldn't wake up again. But Curiosity won't have that problem because Curiosity is nuclear powered. Right? It has the, the thing that Mark Watney went to go get, the radioactive isotope generator, that thing, that's what it uses. Okay, so don't dig up the big bag of plutonium, Mark, right? That whole thing, that's what it's powered by. All right, there's been some questions about whether that's an ethical power source to use, okay? And so we're not using it on every lander. Some of the landers are still solar powered because there's an issue with, hey, let's send this big piece of radioactive plutonium to another planet and leave it there. Well, it's not even so much people living there. It's the ethical part of if there is actually like primitive bacterial life or something like that on Mars, they could be irradiated by the big box of plutonium we sent there. Up here? Okay, this would be Voyager. Okay, because Voyager went by all the outer planets. Okay, this diagram greatly simplifies that trip because the planets are not lined up like this. Okay, they're constantly going around. So the flight path of Voyager went to Jupiter and then had to go across the solar system to get to Saturn, and then across the solar system again to get to Uranus, and that's, by the way, how you pronounce it. Okay, and then across the solar system to Neptune, and then it didn't get a chance to go to Pluto because at that time Pluto and Neptune were on opposite sides. Okay, so it just wasn't, you couldn't make it turn around and go all that way. It would take forever. Yeah, it's on its way out. It's in the Kuiper Belt kind of thing, and yeah, headed on its way out there. Yep, they still get data. It pings every once in a while, and they're actually using that for tracking the influence of the sun's gravitational field, because they know how much it's pulling it or changing its course. So every time it pings, they can detect that course change. And so they're getting a much better idea of how far out the sun's gravitational influence extends. So it's still providing valuable science. Okay, New Horizons at the time of this picture hadn't gotten to Pluto yet. Okay, it was still well inside, but New Horizons is the fastest spacecraft ever built. Okay, it's going really, really fast. And it's, so it was here back when this picture was made. Obviously now it's way out here. It's actually past the Voyager spacecraft. Okay? It's out in the Kuiper Belt, and I don't know that they've figured out whether they're going to pass it by anything else now. Okay? It's very, very far away. Everything has to be done remotely. So they have to decide, when is it going to start taking pictures? When is it going to fire this engine? They have to decide that weeks in advance, and then send that data to the spacecraft that will carry out those instructions without any human control, because it is hours and hours away, okay, at the speed of light, so we can't remotely control anything. What do you mean? Oh, well, it's just the way we designed it. I mean, it's more modern, right? It's got a better engine. It had better gravity assist path, right? Voyager had to go around each planet, right? Like it stopped at every planet, whereas New Horizons got a gravity assist from Jupiter, and that was it. And then it was headed out. All right, so lots to think about, because we're using that same equation, that Fg equals big G times M1 times M2 over R squared, to do all of these calculations. All these gravity slingshot calculations involve that force of gravity. We need to know how much it is. We need to know how much it's going to change and how it's going to alter the course of the spacecraft as it moves along, so that we don't miss our target, right? If you are off by even a degree over these distances, you can miss a planet by a long way. Okay, because we're talking about huge, huge distances here. All right, so we already did that one. So, okay, I want you guys to try this one here. Okay, so Mount Logan in Yukon is 5,959 meters above sea level and is the highest point in Canada. They're giving Earth's mass differently here. Okay, the textbook that I take this out of has a different mass than is on our formula sheet, that's fine. Okay. Same with the radius, their number is slightly different. What would be the difference in magnitude of the weight of a 55 kilogram person at the top of the mountain as compared to its base? Assume the Earth's equatorial radius is equal to the distance from the Earth's center to sea level. Okay, so essentially it's saying in the first situation, calculate the weight of the person with this radius. And then in the second situation, add what to this radius? The height of the mountain. Okay, we want to see how much more or less do you weigh in those two situations. Okay, so that's what we're trying to figure out here. So you're doing two separate calculations using this formula. All right, so give that one a try and we'll go through it here in a minute. All right, so like we said, it's going to be two separate calculations using Newton's universal law of gravitation, so this big formula here. All right, so we're going to first calculate the force of gravity at sea level. Okay, so we'll say SL here. All right, so that's going to mean 6.67 times 10 to the minus 11 times 5.98. Sorry, they have 5.97. We'll use their numbers here. 5.97 times 10 to the 24 times the person's mass, which was 55 kilograms. Then they have 6.38, right? Times 10 to the 6 squared. All right, so this will be our weight at sea level on Earth, okay, for this person. So all right, so the what did I miss? I forgot the 55 kilograms. That's why I got 9.79 entry. Forgot the 55 kilograms in there. Okay, so their weight at sea level is going to be 538.949 or 0.950, 538.950. I know that's not the correct number of significant digits, but I'm just going to leave the number there for now. Okay. All right. So next thing we want to calculate is force of gravity on the top of the mountain. Okay. So basically it's the same numbers, 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24 times 55. But now we're going to have a slightly different radius. We're going to have 6.38 times 10 to the 6 plus 5,959 meters. Okay, and then that will all be squared. So I'm just going to take my entry from the last one, and I'm just going to add that in. Okay, so I'm just going to put another set of brackets here on the bottom. Plus 5959 bracket squared. Okay, so am I lighter? Noticeably? Not really. I'm not going to notice 1 Newton worth of difference between the top of the mountain and the bottom. Though I'm going to be lighter on the top of the mountain because I'm going to lose mass walking to the top of that mountain. Okay, like I'm going to burn a lot of calories. I am going to be smaller when I get to the top of that mountain. So I'll be lighter up for that reason, as opposed to there's so much less gravity on the top of the mountain. No, because it won't give you an accurate enough number. Okay, then we're trying to use this formula here because it gives us a more accurate version of events, essentially. I mean, it's not a whole lot different, but if we were talking about, significant digits, it could make a rounding error, right? And make a difference there. Question? Okay. All right, so even that distance, even just under 6,000 meters, does make a bit of difference in terms of your weight, okay, how much you're attracted to the center of the Earth, because remember, R has an inversely exponential relationship, and that's what that's trying to show. Okay, you know what, I think we'll we'll leave it at that for today. Okay, tomorrow we'll talk a little bit more about this gravitational stuff and talk about Kepler and Cavendish, and then Friday we'll talk about satellite motion. Okay.